Okay, if you've ever had to run, say, massive bundles of coaxial cable over long distances, you know the pain.
Oh, it's an absolute nightmare.
It really is. We're talking hundreds of yards, maybe even a mile. That's our mission today on the deep dive.
And more importantly, how to fix it.
Exactly. How to completely replace that bulky, noisy copper infrastructure with, sleek, hair-thin fiber optics.
A much better solution.
So we've got the specs for a system that really shows this shift. It's the Thor Broadcast F-SattGalaxy-TX 51X16 kit.
It's a bit of a mouthful.
It is, but its whole job is to take 4 dedicated satellite signals plus 1 standard terrestrial RF signal.
And just consolidate them.
Yeah.
And that's the critical thing for you to understand. We're talking about turning 5 or maybe even 9 thick coaxial runs into just one single mode optical cable.
Chilled one.
One. It's not just about distance. It's about solving that information overload problem in these huge distributed environments.
Okay, so let's unpack that. How in the world do you cram 5 completely separate radio frequency signals into a single fiber?
And they're very different signals. You have 4 L-band satellite signals.
Which is that intermediate frequency after the dish does its thing, right?
Precisely after the down conversion.
Right.
And then your 5th signal could be something complex like terrestrial ATSC or even CATV QAM data from a cable system.
So really different kinds of data.
Very different. And this is where it gets really interesting. The system relies on something called coarse wavelength division multiplexing, or CWDM.
CWDM. Okay, so think of it like a highway for light.
That's a perfect analogy. The single fiber is the superhighway, and CWDM essentially carves out dedicated traffic lanes inside it.
So you're not actually mixing the signals, you're giving each one its own dedicated color of light.
That's exactly it. Multiple signals right at the same time, but each one is carried by a separate laser on its own unique, non-interfering wavelengths.
And the transmitter handles that automatically.
Yeah, it does. It has 5 built-in fixed wavelengths, 1510 nanometers, 1530, and so on. You don't need to memorize the numbers, but the fact that they're fixed is what guarantees predictable performance without any crosstalk.
You know, the biggest headache with traditional COCOS, especially over distance, is just signal loss, degradation, and electrical noise.
Oh, absolutely.
By isolating each signal onto its own light path, I have to imagine that whole logistical problem just disappears.
It pretty much does. That isolation kills the signal degradation and all that electrical noise you get with long copper runs. That's a huge cost benefit, honestly, maybe more so than just the distance.
Really?
Yeah, I mean, just think about a bundle of 5 COCOS cables running 10 kilometers. The weight alone is hundreds of pounds. You need conduits. The labor is immense. Moving to one fiber strand is a massive win.
And speaking of distance, the specs say the system is designed for some serious range.
That's right. We're tight distribution up to 10 kilometers. And the scalability is, well, it's huge. The transmitter has a high optical output, so it can feed up to 32 optical receivers. So in a large MDU, a multi-dwelling unit, or a campus, you could easily be serving over 1,000 total outlets, 1,000 subscribers.
Wow. Okay, but that's a lot of critical data writing on one, hair-thin wire. Doesn't that just consolidate all your failure points into one spot?
That's a valid concern, it is. But the engineering is really built for reliability. For instance, it has built-in automatic gain control, or AGC.
Right, AGC.
Which, for anyone managing this, means the signal output stays stable even if the input fluctuates a bit. You're not constantly running around trying to tweak the system.
Okay, that makes sense. And what about the physical connections? I noticed the specs call for SCKPC connectors. Why does that angled physical contact part matter so much?
That is a crucial detail. When you're using powerful lasers, any light that hits a flat connection point can reflect right back into the laser source.
That would destabilize the whole signal.
Severely. The angled cut of that APC connector physically prevents that reflection. It just makes sure the signal transfer is as clean and lossless as possible. It's a small detail, but over 10 kilometers, it's essential.
So, to summarize the big takeaway here, this technology is standard 1 transmitter to 16 receivers in this kit is basically the answer to congestion, distance, and noise.
It just eliminates the mess. It's sort of the physics problems that come with long-haul codes.
Yeah.
So what this all really means for you is that the ability to compress 4 satellite feeds plus other RF data onto a single fiber stretching 10 kilometers, it just shows the irreplaceable role that WDM plays in modern digital infrastructure.
It's just fundamental at this point.
It is. And here's a final thought for you to consider. This specific solution costs around, what, $12,150?
Right, around 12 grand.
So ask yourself this. What level of sheer physical complexity? How many hours of labor, how many amplifiers, how much conduit must a traditional copper installation have to make that $12,000 price tag a genuine, significant saving?
That's the real calculation.
That's the power of high-density fiber technology.